Hi guys, welcome to lesson 2 for this unit. Hopefully everything went okay with the last lesson. It looks like most people's homework was up to date and good. I will be contacting you individually if I need to. Otherwise, please feel free to contact me if you need any help. Okay, let's get started on today's lesson. It's quite long, I apologize, but it's one of the more complicated or complex lessons within this whole year. And so it's important really to pay attention, and because we're going to bring several concepts together, and in the end it should all make sense, but at times you may be slightly lost. So I've given you, please obviously print out this handout, but I've given you this table to fill in, and if you want, just to save time, you can just copy what I've written here. Basically, what I wanted you to do is just to type into your calculator the sine of all of these angles. So all of these angles and the cosine of all of these angles, and the same with the other side of this table, and fill in all these values. And what I wanted you to see is to look for patterns and look for values that are the same for sine in different angles and the same for cosine. And we kind of touched on this when we did the ambiguous case of the sine law. Remember how we did the inverse sine of something and we got two possible answers? And there's a reason why we got that. And hopefully today's going to explain why and expand on it. So for example, number 2, it says what angles for sine have the same value as sine 45? So sine 45, let's just write it down, is equal to, if we go to our table, that's this guy here, 0.707. So approximately 0.707. If you peruse your table and look around, it looks like also sine of 135 is 0.707. So they're actually the same. And that's consistent with the ambiguous case. And what I want you to think about is, what is the relationship between these two numbers? And so are there any angles that have the same value but at different sign, i.e. are they negative? So if we go to the right side of this table, if you look, we have the sine of 225 gives us a negative, and also the sine of 315 also gives the negative. So sine of 225 equals the sine of 315. Or you could think of the sine of 45 is equal to the negative version of sine of these two angles. So if you tally those all up, we've actually got 4 different angles matching up, although the signs do differ. So sine of 45 matches up to 3 other ones with the signs somewhat different. And we're going to try to explain that. But we have to start talking about some language and vocabulary. And so if you think of what these things are, what we can call one of them, the 45 degrees, is what's called the related acute angle or the reference angle. And generally this is given the symbol alpha, which is this little fishy guy. So alpha looks like this. And it's just an angle that's less than 90 for which you'll have a bunch of values similar to it. So we have to start thinking about drawing angles, not just flat on the surface, but in kind of in a space, in a quadrant system. And that's what we're going to be shifting towards. So if we use our chart above and our calculator, let's find the cos of 300. So cos of 300, according to our chart, is equal to 0.5. So that's this guy right here. And it says determine a related acute angle for that. So we would have to go on our table, and if you look for cosines, you will find that there's a related acute angle. It looks like, I'll do it in a different color, cosine of 60 also has that value. So what we want to do is to visualize this. And so obviously 60 degrees, we can draw that quite easily. But the 300 degrees, what we need to do is think of in our quadrant system. And this is a bit different than when we were doing bearing, where we had direction. But if we think of the x-axis as 0 degrees, And if I rotate counterclockwise, so the top here would be 90. So from here to here is 90 degrees. I'm just gonna get rid of that. If I keep rotating over, then this is going to be 180. This will be 270. And if I were to rotate all the way around, so do one full spin, one rotation, I would end up back where I started, which is 360 degrees. So where would the value, or where would 300 degrees land? So if I was rotating counterclockwise, I would go like this, and I would end up between 270 and 360, somewhere like this. And what we do is we draw in a standard position, and we're going to write this down in a minute. But a standard position means you start at the origin and you draw it out. So this would be like the hypotenuse of the triangle, and the triangle would connect to the x-axis. And so that what I've rotated around, this thing, the blue line that rotates around, that's my 300 degrees. So if you were to spin 300 degrees, you're almost back to where you started. How does that relate though to this 60 degrees? This is where this related acute angle, alpha, or the reference angle, is. That's this angle from this hypotenuse to the x-axis right there. And so alpha in this one could be calculated by simply, if you look at this, how does 60 relate to the 300 and the 360? Well, we can take 360, subtracting 300, and that determines my related acute angle, 60. Let's try another one. Again, we're going to do this a bunch of times, so hopefully it'll make sense. This one's more like what we did with the ambiguous case. So again, if I draw this from the x-axis rotated, counterclockwise, I'm going to end up here. So I draw my little standard position hypotenuse, and I connect that hypotenuse always to the x-axis, never to the y-axis. And so that this thing, and it doesn't have to be accurate, but this is about 150 degrees. So the question is, what's the related acute angle? And so alpha in this case will be, if you think of this being 180, alpha is going to be the difference between 180 and 150, which gives me 30 degrees. And so if you look back to our table, we should find that sine of 150 is equal to the sine of 30, which it is. And both of these are equal to 0.5 or 1/2. They just happen to be the same as part A, but that's just coincidence. So always in these cases, you're always going to have another angle that's going to be referenced. And knowing these different things is going to be really important. So some language before we move on. So again, as I said, we're moving away from just thinking of angles in space towards angles in some quadrant system. That allows us to look at angles in a bigger context, and we'll explore that in this unit. And so we can plot points in space with the origin as the reference point, and then we connect a line just like we did, creating what's called the terminal arm. Another name for the terminal arm in all of these is just the hypotenuse. And we'll create an angle that connects to the x-axis. So the initial arm, although not really that important, it's really just the x-axis, and that it is important in terms of how you start this, but the name of it doesn't really matter. So this is my initial arm, so where I start my angle. My terminal arm is the line where the angle finishes. And so it could be just in the first quadrant, but it could be in any quadrant. And again, that's the hypotenuse of the triangle formed. So this guy here is my terminal arm. And how we get an angle out of this is that we take the terminal arm and we connect it to the x-axis like this, so that it always forms a 90-degree triangle. And so the angle in standard position is generally given as theta. And theta is the angle that starts at the x-axis, or the initial arm, and then moves counterclockwise. And ends up finishes at the terminal arm. So from here to here would be my theta. And if it's actually in this first quadrant, so this is quadrant 1, quadrant 2, quadrant 3, and then IV, which is quadrant 4. If it's in quadrant 1, that's also actually, this angle can also be alpha. And that's this thing here, which is the reference one, which we talked about. So the reference angle is the related acute angle denoted as alpha, measured from the x-axis just to the terminal arm. If this triangle happened to have an angle greater than 90, let's say it was between 90 and 180. So if I draw something here and I connect it down, I would now have theta that goes from the x-axis. This is my angle in standard position. I'm going to call it theta here. But now my alpha is the angle that's the related acute angle from here to here. So you can continue that in all of the quadrants. And so I'm just going to complete this little drawing, and you can draw this in. So you end up always forming one part of this shape. And if you look at the shape, there's different thoughts about what it looks like, but you can guess. If I was to ask you, what does this thing look like? Some people might say, oh, well, a butterfly, a bow tie maybe. For those Star Wars fans, maybe it's an X-Wing fighter. That's what I see. But you're always going to form what's part of the bow tie. You are never going to connect this hypotenuse, let's say we're looking at this one, to the y-axis. That is wrong. It's always going to be connected to the x-axis. So if we look at that kind of thing, so if we start here, I'm just going to do something similar. I'm just going to add things to this. What we can do is think of, this is my point from my terminal arm. And we're going to use what's called the unit circle. So the unit circle is a circle that has a radius of 1. And again, there's a lot of concepts that are going to come together, but hopefully it'll make sense once we start doing things. But you really need to follow along and think critically as we do this. So if I think of this as point P on the circle, it has a value, let's say, of x and a value of y for its height. So x is my horizontal. I still create a quarter of my bow tie. That's awful. Let me fix that. I'll just put it here maybe. There we go. So I still create that. My height is y. My horizontal is x. This inside is my alpha, and my radius is my hypotenuse, which is r. So I can create this in all of the 4 quadrants again. Maybe I'll make that more even. So let's say I've got a point P. I go from my terminal arm, or my origin out, and that's my terminal arm. This is P. And this time P, when I connect it, notice my value for x is going to be in the negative quadrant. So I have negative x, comma, y. I still have r, I still have y, but this is negative x. And my little fishy there guy is alpha inside. And I can do the same thing for the other quadrants, creating my X-Wing fighter. And so this is P. Now I've got negative x, but notice when I go down here, I've also got negative y. And you'll see why this is important in a few minutes. And then the last quadrant, again, I'll just finish these so they show the 90 degrees. This is r, this is still negative y, but now I've got a positive x. So this is the point P where it's x comma negative y. So when you look at this, if I was to put in here, first I'll put in my alphas. So those are the related acute angles here, 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 and here. If I was to find sine of alpha, it doesn't matter which quadrant I'm in. Sine of alpha, sine is always the opposite over hypotenuse. In all of these, that's going to be y over r. What's going to happen, though, is that sometimes y is negative. It depends which quadrant we're in. Cosine in any of these of alpha is going to be the adjacent side relative to alpha, which is x, and my hypotenuse is r. And then tan is going to be opposite over adjacent, which is y over x. So this thing, you're always creating a quarter of the bow tie when you draw these things, and we're going to try to use that to find the related acute angle in a question here below. Okay, so it's coming together a little bit. So let's determine the reference angle or the related acute angle, which is alpha, for these angles. So let's just sketch them. So if I draw 335 degrees based on an angle in standard position, that means I'm going to draw it from the x-axis, rotate it around, and it's going to end up in this quadrant. Oops. So that this is 335 degrees. What I want to find is what is this thing. And for most people, hopefully you're able to figure this out without using any sort of algorithm. And I'm just going to fill in here. All of these axes represent certain angles. So I go from 0 to 90 to 180 to 70 and all the way to 360. So in this case, alpha, the easiest way to find it is going to be to take the bigger angle, which is 360, subtract the 335. Which in this case is going to be 25 degrees. And that's my alpha. So if you can, I would try to draw all of these yourselves first. So I would pause the video, see if you can get it, and then if you want, skip ahead. So I'm going to draw them out, and I will explain a couple of them, and then I'll just draw the rest. So 260 is going to land in the third quadrant, somewhere here. Create my quarter of the bow tie connecting to the x-axis. This is 260. Alpha, the guy inside, is going to be the difference in this case between bigger angle and 180. You're always going to be using either 360 or 180 in your calculation. So this one's just going to be a difference of alpha. It's going to give me 80 degrees. Similarly, this one, 170, is going to fall in quadrant 2, almost to the 180 mark. So alpha, again, the difference between 180, the bigger one, minus the smaller one, gives me alpha of 10. So hopefully you're getting the hang of this. If not, that's okay, you will eventually. Being able to draw these is really important. So 225 minus 180, always referencing 180, never use 270. So this one's going to be the difference of 45 degrees, which is one of our special angles. And then the last one's a bit trickier. It's 370. So that means I'm going wrapping around, doing one full rotation, and then going a little bit extra beyond. And so this one we're going to talk about more in the next class, but oops, that should be 370. I'll just do this, 370. And so what alpha is what's left over. And this one's a bit trickier. It's the difference between 370 and 360. So it means that I've rotated one full rotation and then gone an extra 10 degrees. So there should be something located here, but I think I can get to this. Let me see. Yeah. So the next question says, as a class, use this application. So I think there's a link. Otherwise, you can just follow along. But you can kind of ignore these graphs, but what I want you to look at, and this is kind of get resized, is to look at, as I move this along, if I can move it, maybe it's not going to allow me to. Oh no, maybe I can refresh. Maybe not. Anyway, we're about where I think we want to be. It says find the value of sine 230, tan 230, and cos 230. What I want you to see here is that, and I can't really write on the screen, but if you look at the tan there, you've got a negative over a negative, which ends up as a positive ratio. The sine, we have a negative over a positive, which gives me negative, and cosine is negative over a positive. We want to answer why is that the case. So it says find that. First time, let's just sketch it so we have it there. So if I sketch that, 230 somewhere over here. So that's 230. And remember that sine is y over r. Cosine is x over r. And tan is y over x. When you look at this, what we have is, because we're in this quadrant, quadrant 3, this is going to be a negative y value and a negative x value. But r, the radius, will always be positive because radius is something that's being squared when we think of Pythagorean theorem. So in this case, y over r is going to be a negative over a positive, which is going to equal a negative number. Cosine is going to be, again, x is negative, r is positive, that's going to be a negative number. But tangent is a negative divided by a negative in this quadrant, which ends up being positive. So I was hoping to show you in the application, but as you rotate between all of the 4 quadrants, these values for sine, cos, and tan will change signs based on which quadrant it's in. So if we were to explain it, 230 is in quadrant 3, where x and y are negative. And so, therefore, sine and cosine are negative, but tan is positive. So what this creates is, depending on the quadrant you're in, and here's a little infographic for you. Let's start in quadrant 1. So if you look at quadrant 1, in this quadrant, x and y are both positive. As a result, all of sine, cos, and tan are positive. So quadrant 1, we say that all, or A, all of them are positive. If you go to quadrant 2, this time y is positive but x is negative. As a result, in quadrant 2, we end up with sine as being a positive number, but cosine and tan are negative. So we call this the sine quadrant, or S. So sine is the only one that's positive. If we go to quadrant 3, this time y is negative here, and so we end up, and x is negative rather, and so we end up with sine and cosine is negative, but tangent, as we saw above, becomes positive. Because tan is the positive one here, we call that the T quadrant. And then if we keep going, in this quadrant, we've got X is positive, but Y is negative here. And so sine ends up negative and tangent ends up negative. And so because cosine is the only positive, we call this the C quadrant. So if you spell this out, it spells Astica, but rather than saying that, we start at the bottom right and call it the cast rule. So what the cast rule tells us, it's a mnemonic that tells us which trig ratio is positive or negative in which quadrants. So it tells us which trig ratios are positive or negative in which quadrants. So if we were in class, I would just yell out, okay, we're in quadrant 2, what's positive? And you would look and you would say, okay, now sine is positive. Again, if I said quadrant 4, you would look and that's the C, that means cosine's positive and sine and tan are negative. We're gonna use this rule, and with this explanation, we don't always have to explain it, but with that rule, we can figure a bunch of things out, and that's what we're gonna do now. So we're gonna take all of these concepts and put them together. So, first one says, solve cosine of theta is equal to -1/2. So -1/2, you could start this question in two ways. I'm going to start it by thinking about what this negative tells us. So the negative for cosine, so a negative for cosine indicates what? It means that this angle theta has to be in which two quadrants. So if you look at where cosine is negative, that's this S and T quadrant. So that means quadrant 2 and quadrant 3. So I can automatically draw two angles in standard position, one in quadrant 2 and one in quadrant 3. So I automatically know that I'm going to have an angle from here to here. I'll call that theta 1. And I'm going to have a second angle from same starting spot from here wrapped around to there. So that's theta 2. So that's one good place to start. So what we need though is what is alpha? And there's two ways to figure this out. One is you could rely on your calculator, but because you guys are smart, let's not do that. If it's the ratio of 1/2, 1/2 comes from one of our special triangles. And not always will these come from the special triangle, but you remember 1, 2, and root 3? This is 30, this is 60. So if I was to try to figure out where this came from, cosine of which one, 60 or 30, would create 1/2. So that's one way to do it. And what you would find is that gives you the alpha. So you could simply use your special triangle to figure that out. And the answer is 60. The other way to do this is to also just rely on your calculator and you punch it in. And you punch in the positive version to get the related acute angle. If you don't use the positive version, it won't work. So I take the negative away and I punch that in and yeah, we get 60. So that tells me the related acute angle. And then so now I need to look at my diagram and say, okay, well theta 1 relates to the related acute angle by saying 180 minus that related acute angle. So if I do that, I get 120. That's one of my answers. That's a possible answer for theta. So the second one, I take, because I'm in quadrant 3, I take 180 and I add the 60. So I get 240. So I get two possible answers. So hopefully you're thinking, oh, well, this is really similar. Maybe you're not thinking that, but this is really similar to the ambiguous case for sine law. And it really is. We're using this information in order to figure out two angles, but we're also including the cast rule and we're including our special triangles. There is a little algorithm chart here. If you're in each quadrant, you can use this, but I think it's better to just simply rely on your visual of this diagram here and figure out from the diagram. I think that's better than memorizing a formula. Okay, let's try a couple more. So this one says solve for all possible values of theta where it's between 0 and 360. So again, we've got positive 1/2. So even though it's not written, this is a plus. So that tells me sine is positive. Where is sine positive? So I say, okay, well, sine is positive using the cast rule. Sine is positive here and here. So that's quadrant 1 and 2. So that's part 1. So if you want, you could draw your triangles knowing they're going to fall there. So the second part is to find what is the related acute angle, so alpha. And again, if you go to your triangle, this is actually another one of our special triangles. And this one, sine of 30 would be 1/2. So again, you can use your calculator. Inverse sine of 1/2 gives you 30 degrees. So that means one of your answers, theta, let's call it theta 1, is going to actually just be 30 degrees. The second angle, though, is going to wrap to that second terminal arm. We'll call that theta 2. So theta 2 is going to be 180 minus 30, which is 150. There's our two answers. Not too bad. So the second one here, we've got cos theta is negative 1/2. So again, let's first start by thinking, where is cosine negative? So CAST, well, cosine is negative here and here because it's positive in the C and all categories or quadrants. So this is quadrant 2 and 3. So you can automatically draw this. So I would expect you to be able to draw this. I wouldn't expect you to write quadrant 2 and 3, but you can if you want. So now I need to think about what the related acute angle is. And again, if at any point I would pause this and try to figure this out yourself. So this comes from the other special triangle where I've got 1, 1, and root 2, and these are both 45. So alpha in this case is 45 degrees. So that's my related acute angle. So what we need is theta 1 and theta 2. So theta 1 is just going to be my 180 minus the alpha, which is 135. And theta 2 will be 180 plus alpha. Comme ça. All right, why don't you try the next two, because I think you probably can figure this out. So pause the video if you need to. Otherwise, you can follow along if you're still needing more help. So this one, I've got tangent, so CAST. Tangent is negative where? Well, that's quadrants 2 and 4. So that's here. Oops. 2 and 4, because it's positive in the other two, in A and C, or A and T rather. So I've got that. Again, if we use a special triangle, or you can use your calculator, you find that alpha is 60. So tan of 60 is root 3. So that means this is 60, and this is 60. I'm just drawing it slightly different than I did. I didn't put the alpha in, that's okay. So theta 1 is 120. Theta 2, now we're into 360 minus alpha. Because we're in quadrant 4, we take 360 minus, which becomes 300. And there's our two answers. So it's two angles between 0 and 360 that satisfy that. So again, this one, similar to what we had before, only now it's positive for cosine. Positive here, so that means we're in these two quadrants. So I'm not going to write out which quadrants. and it's root 3 over 2. That means that if I draw this, so alpha, in this case, alpha is going to be 30. You can use your calculator to double check. So my first angle, theta 1, is the related acute angle. My second angle, which wraps all the way around, theta 2, again, because we're in that quadrant, we're going to use 360, and I end up with 330. So there's a lot going on in these questions, and you really have to think about it in several ways. One is the cast rule. Another is, which values for your related acute angle are you going to use, and then you have to figure out your thetas based on your drawing. Okay, next question is a bit different, although similar concepts. This one says determine another angle that has the same trig ratio as each angle given. So tan of 20. So if I draw 20 degrees, let's say that's 20. Where else am I going to have a ratio? It doesn't say what is the ratio. It says determine another angle that has the same ratio. Well, I know if tan 20 that it's positive. So this is going to create a positive for tan. So that means I'm in this quadrant. Where else is tan positive? That's here. So what I need to do is think, okay, my related acute angle is 20 because they give it to us, because it's in that quadrant. So my theta, the one that goes from here to the terminal arm, is going to be 180 minus the 20, 200 degrees. That means tan of 20 is equal to tan 200 degrees. And you can always double check that on your calculator. Second one is 115, so it's sine. So we're somewhere here. So from here to here is 115. So if I wanted to find alpha first, so this is what we're going to need, I can take 180 minus 115, which is going to give me 65 degrees. So that's part of it. But we also need to know where else am I going to get a sine that's a positive angle. So if we think of it, the only other place is in the all category where everything is positive. Sine, cos, and tan. So I've got this. That means alpha is the angle, so theta equals alpha in this case, which is 65 degrees. So again, you can double check. Sine 115 is sine 65, which is the related acute angle. Okay, the next one, it says use a calculator this time. Because we don't have exact values, we've got decimals and stuff, to determine all the possible values. So in this case, if I wanted to find the first angle, I would simply use the inverse sine of this. And that gives me an angle. So that's going to be approximately, if you punch that in, 55 degrees. Then you have to say, okay, well, this is positive for sine, right? Where else am I going to have an angle? So that's in quadrant 2. So in quadrant 2, I take 180 minus the other angle. So it's approximately 125. The second one here is a bit trickier. So we're going to use our calculator to find one answer. So if I punch this in, inverse cos of 0, I get 90. So this is an irregular triangle because at 90 degrees doesn't really work for SOHCAHTOA. But what you need to think of is, so I've got 90 here. What that means is from here to here is 90 degrees. So that's fine. But recall that cosine of any angle is x over r. If I had a value of 0, so 0 here, that means the only way I can have this work is x is equal to 0. So if you imagine your unit circle, when is x equal to 0? Well, one of them is 90 degrees. The only other time x is 0 is if I'm down here at 270. And so my second angle is 270 degrees. And we're going to talk about those special cases a bit more later. I wouldn't worry too much about them, but it really refers to the X and Y and which quadrant is positive and negative. So the next one is tan theta. When I want to do the inverse tan of this, what I should do is find the related acute angle. So I should rewrite that. This should be alpha. Alpha is going to take the positive plus version of this, and that's going to give me my related acute angle, which is approximately 85. So knowing that this is negative, where is tan negative? If you need to, you can draw it out. So tan is negative here and here. So that means theta 1 is going to be 180 minus 85. So I end up with approximately 95 degrees. And then theta 2 is wrapping all the way around. So I got 360 minus 95 degrees. And so I end up with 265. Like that. Okay, this is not an easy lesson. As I said, please, if you need to, go back through certain questions and re-listen. Otherwise, try out the questions here. I've got all the solutions. And that's your homework for today. And we will pick up this stuff next class and talk about it then. Okay, I hope everything's going well for you.